Because water is so central to living things, we use terms that center around water to describe the relationship between solutes and water. So for example, hydrophilic means water loving, and this term is used for anything that easily dissolves in water. And remember, that means because of like dissolves like, that means ions, so charged atoms and molecules, and anything that has polar covalent bonds will dissolve into water. Hydrophobic is the opposite. It means water fearing. These are things that don't dissolve easily in water. Anything that's non-polar will not dissolve into water, and the classic example of this is oils. The third term is amphipathic. Maybe this sounds to you like a word you already know, amphibian. Amphibian means lives on land and in water, and that's kind of what amphipathic means. It's molecules that have parts that are hydrophilic and parts that are hydrophobic, or in other words, it has parts that like to live in water and parts that don't want to be in water. So they have both polar and non-polar regions. Amphipathic molecules are really special because they do have these two parts. They're going to be able to exist in the boundaries between water solutions and non-water solutions. And they're going to do this by forming micelles. So we'll take a look at a micelle. So I'm going to draw for you here an amphipathic molecule. So they typically have a region that's polar hydrophilic, and it's often referred to, and especially what we're going to talk about, as a polar head region. And then it has part of it, and that's this bottom part here, that is nonpolar, and therefore would be hydrophobic. So part of it is hydrophilic, this side of it, and part of it is hydrophobic. Okay? Because of this, again, this part will not want to be in water. This part's okay with being water. This part really does not want to be. So if I mix oil and water, okay, think about that. If you mix oil and water, they might look mixed for a minute or two, but as you probably know from experience, the oil and the water will separate. If you add soap, things change a little bit. And again, from experience with dishes, you probably know that if you add soap, that's going to make the oil seem to go into solution better. And that's useful when you're washing dishes because that'll allow you to wash away the oil. The reason why soap changes the relationship between oil and water is that detergents are amphipathic. So they have this dual nature. So what will happen is that the amphipathic molecule, the detergent in this case, will surround the oil. So this is going to be some oil. So I'm just going to put a circle around it. So it's globs of oil. And when you mix oil, water, and soap, the soap will line up around the oil, surrounding the oil. Whoops. Sorry, messed up my drawing there a little bit. Okay, and out here is water. So all the rest of it is water. And notice that the way I've drawn the micelles, the hydrophobic part is facing the oil. This is okay with being away from water, but this polar head group is facing the water. So now this oil is in this little bubble that's going to allow it to be dispersed into the water, and so I can now wash it away when I wash the dishes. And this is the image from your textbook. So again, just to add on to here, there's oil here, there's water out here, and these are your amphipathic molecules that are putting their hydrophobic regions near the oil and their hydrophilic regions near the water. This idea, the way that amphipathic molecules surround the oil, or the way that they can be an intermediate between water and nonpolar regions, is going to be really important when we talk about membranes in Chapter 5, because amphipathic molecules will help establish the boundary between the cell and the environment by creating this kind of structure, or a related structure called a phospholipid bilayer. And we'll talk about that a lot more later on in the semester.